On October 29, 2018, a brand new Boeing 737 lifted off from Jakarta and climbed out over the Java Sea. Within seconds of takeoff, an invisible force began fighting the cockpit crew. The captain pulled the control yoke back to raise the nose, but a mechanism forcefully pushed it down. This mechanical tug-of-war repeated more than 24 times. Outside the plane, a single angle of attack sensor was misaligned by exactly 21 degrees. It fed an extreme Fahrenheit trajectory into a flight computer that trusted the reading absolutely. The system driving the aircraft toward the water was not broken. It was executing its programming exactly as its engineers intended. The entire struggle lasted exactly 189 seconds. The resulting impact claimed the lives of all 189 people on board. Aviation engineering requires backups for every critical component, yet 2 of the most advanced commercial jets ever manufactured were brought down by a single point of failure. The catalyst for the 737 MAX was a business threat. Airbus launched the A320neo, a highly fuel-efficient narrow-body jet that aggressively cut into Boeing's market dominance. Instead of spending billions and several years engineering a new airframe from scratch, Boeing strapped larger, more efficient engines onto the aging 737 chassis. This side profile diagram illustrates the aerodynamic consequence of that retrofit. To clear the runway, those larger engines had to be mounted further forward and higher up on the wing. In steep climbs, this weight distribution caused the nose of the plane to pitch upward. To counteract this, engineers wrote a software patch called the Maneuvering Characteristics Augmentation System, or MCAS. When the system detected a steep climb, it sent a digital command to the rear horizontal stabilizer, automatically forcing the nose back down so the plane flew exactly like older models. The pilots would never notice the intervention. But the code harbored a fatal vulnerability. MCAS pulled its reading from only one angle of attack sensor at a time. Despite the aircraft having 2 sensors, the software completely lacked a cross-check mechanism. By granting absolute, unquestioned authority to a single data feed, engineers turned a manageable aerodynamic quirk into a lethal trap. Boeing's sales pitch to airlines hinged entirely on continuity. They promised that pilots stepping into the new MAX would require only a few hours of iPad-based instruction, completely bypassing expensive flight simulator training. Protecting that promise dictated how the software was classified. In a 2013 internal memo, Boeing employees actively agreed to downplay the extent of MCAS to regulators. If they admitted the system had significant flight-altering authority, the FAA would have mandated the very simulator training Boeing needed to avoid. This aggressive cost-saving strategy extended to the cockpit instruments. An alert light meant to warn pilots the M2 angle of attack sensors disagreed was left inoperable on most of the fleet due to a software glitch. Crews were flying completely blind to the lying sensors. This timeline visualizes the catastrophic assumption at the core of the MCAS safety case. Engineers determined the system was safe because they assumed a trained pilot would recognize an uncommanded misfire and respond within exactly 4 seconds. Internal simulator data showed a starkly different reality. When a highly trained Boeing test pilot was subjected to the exact same misfire, it took him more than 10 seconds to diagnose the issue, a delay he explicitly labeled catastrophic. The inherent danger of the MAX was a mathematical reality, explicitly documented and ignored by the company years before the first aircraft entered commercial service. Following the Lion aircraft, Boeing and the FAA circulated bulletins reminding pilots how to disable the runaway trim. They did not ground the fleet. They didn't rewrite the code. They left the single sensor vulnerability intact. Behind closed doors, the FAA conducted its own internal risk analysis. Their models predicted that if the software remained unpatched, the 737 MAX fleet would experience up to 15 more fatal crashes over its lifespan. 5 months later, Ethiopian Airlines Flight 302 took off from Addis Ababa. Almost immediately, a single angle of attack sensor failed and began feeding false data to the flight computer. Unlike the Lion Air crew, these pilots knew MCAS existed. Following the newly issued instructions, they correctly identified the runaway system and reached for the switches to cut electrical power to the stabilizer trim. But the emergency checklist did not account for the physical state of the aircraft. At high speeds, extreme aerodynamic pressure on the tail made the manual trim wheel physically impossible to turn. Even with complete information and perfect adherence to the emergency procedure, the pilots lacked the mechanical leverage to save the aircraft. Within days of the Ethiopian crash, aviation authorities worldwide grounded the 737 MAX fleet. The plane sat idle on tarmacs for 20 months. When global regulators finally mandated fixes, they required Boeing to program MCAS to read both sensors simultaneously, restrict its ability to fire repeatedly, and ensure human inputs always override the computer. These mandates did not require novel engineering breakthroughs. They are the oldest, most basic principles of aviation design: physical redundancy, strict operational limits, and definitive human command. The 2013 internal memo, the catastrophic simulator tests, the survival of the precursor flight the night before Lion Air, the FAA's own mathematical prediction of 15 crashes. Each of these moments represented a clear opportunity to intervene and stop the planes from flying. A single angle of attack vane did not cause this tragedy. Aviation inherently accepts that physical components break. A structural failure of this magnitude is the culmination of deliberate corporate decisions. One by one, those choices quietly stripped away every layer of engineered safety tolerance, until only the disaster remained.